Hello, Algebra students. Mr. Record here from Avon High School. We're talking with our College Algebra 2 class once again in period 6 on our second day of our journey into logarithms, and today's topic is focusing more on what the properties of these little guys, what kind of properties they have. And our big objective, if I could get my pen to work, our objective today is to simplify some complex logarithm expressions by applying all of these properties that we're going to be discussing. So it's a really simple objective when you think about it. And it's all based on something that we have already learned probably in an Algebra 1 class. Let's read these. Two exponential expressions can be multiplied only if their bases are the same. In that case, what is it that we do with the exponents? In one word. Add. Very good. We add. Now, if we have a hard time seeing that, basically what this is saying is that if you have a raised to some power m, that's multiplying by a to some power n, we know that we just take that base and then add the two powers together. You might think, well, what does this have to do with logarithms, right? I don't see a logarithm written here in this blue. Well, wait and we'll see. Now, by the same token, two exponential expressions can be divided if their bases are the same. If that is the case, what do we do with the exponents then? And of course, the answer is subtract. And if you'd like to see some concrete evidence with this, I'm probably going to have to write it over here because I don't have a lot of room. But if I have a raised to the m divided by a raised to the n, we all know that that's a to the m minus n. Now, we don't want to forget those because those are going to serve as the foundation of our first two properties with logarithms. So it says in example 1, let's use our calculator. Let's find the value of each of the following logarithm expressions. And I think what we're going to do here is we're going to do parts A and B together. Okay? And then I will pause the video and we can see how you guys do with C through F if you want to check your answers. So it says use the calculator. Use the calculator. Find the value of each of the following expressions. So we're going to take the log base 3 of 9 and add the log base 3 of 3. So if I go to my calculator, which is somewhere, here it is. Now I'm taking the log, so I have to hit Control 10 to the x, base 3 of 3. Now if you're sitting there and like you have a calculator in front of you that doesn't have a log button that lets you put the base in, hold up and I'll show you what your alternative is. And then let me finish this first. And you guys, was this the log base 3 of 9? Is that right? Okay. I'm going to make sure that I put a decimal point after one of these numbers so that I can get decimal output. And the answer I get is 3. Well, that's interesting. Okay. That's interesting. So I'm going to go back to the document, and I'm going to say that this answer is 3. Okay. Now, for those of you at home that do not have the ability to take a log in base 3, you might want to watch my video over introduction to logarithms, but we talked about how you can get around that by just simply using a common log. In fact, using a quotient of the common log, and you would take the log base 10, so I don't put anything in this field here at all, and you would take 3 on top, and then we would do the log base 10 of 3 on bottom, and that takes care of this first expression. And then to that we would add a fraction where we have the log base 10 of 9 on top over the log base 10 of 3. I'm going to make sure there's a decimal in there somewhere, and this should give you the same answer. But it's a lot more pushing of buttons, right? It's wonderful if you all have a calculator that actually will let you input a base other than 10. Okay? Now I'm going to get rid of this now so it doesn't get in our way, because I need to do another thing, and that is to find the log base 3 of 27. Well, what do you think this answer is? It looks like it's 3, right? So both of these are 3. Now, to my class, do you guys see a rule that's starting to form? Whenever we add like logarithms, of the same base, what is it that we can do to these numbers? It looks like we multiplied them, didn't we? Okay. Do you see how that is this exponent rule in reverse? In other words, whenever there's addition here, we've got multiplication here. That's what's happening. We're just working this rule backwards because logarithms are just the inverse of exponentials. All right? All right, I'm going to do the same thing with this guy. With part B, it says, take the log base 2 of 32 and subtract the log base 2 of 4. Compare that to the log base 2 of 8. So if we go to the calculator, I will take the log base 2 of 32, and I will subtract the log base 2 of 8. Is that what it was? Make sure I put a decimal in there, and I get 2 as an answer. How does that compare with the log base 2 of 4? And we see that it is the same. Both of these answers are 2. Okay, is there another rule in effect? Whenever there is a subtraction going on between your two like logarithms, what is it that you do with these numbers, 32 and 4? We divide them. And that turns out to be our first rule. All right. I'm going to go ahead just briefly. I'm going to pause the video and allow any of you watching the video to compute C, D, E, and F. And I'm going to ask that my students do the same. And then I'll join you both in a moment and we'll check our answers. And as you can see, we are back. If you want to check your purple, or at least my purple answers with what you guys may have worked out, you're welcome to do that. And then I need to go back to B because, yes, I screwed up. I think if I go to my calculator, I accidentally misinterpreted this as the log of 32 minus the log of 8. So let me highlight that. And if I correct that, this should have been a 4. So the answer should be 3. And lo and behold, the log base 2 of 8 should be 3 and not 2. That doesn't make any sense, right? What I had here would not be accurate anyway. So these should be 3s. I apologize for that. So based on our observations with these calculations, let's make a conjecture on how to complete the following properties of algorithms and then write in words what the property says. Well, I'll tell you what, we're not going to write in words. I don't think we're going to need to do that. I would rather us really feel confident about what we put in these blanks, and that'll be fine with me. So if you have the log of any base of m plus the log of that same base of n, how is it that we can simplify this? This would be the log base b of m times n, right? And maybe we put the m times n in parentheses to make sure that all of that belongs in the logarithm. It's all the argument of the logarithm. And then if we do the same thing for these natural logs, the natural log of a plus the natural log of b is just the natural log of a times b, right? You can write more than one logarithm as a single logarithm, okay? Now, that reminds me of a story. You ready for my story? Very few people know this, but Abe Lincoln was a very good mathematician, right? Abraham Lincoln, our 16th president. You're familiar with him? Okay. And in his spare time, he would work a lot of exponential algebra problems and logarithmic algebra problems. And one of his favorite ones was to take a very long expression like the log in base 10 of c and add it to, say, the log of a plus the log of b plus, let's say, the log of the variable I plus the log of the variable n. And he would think about how he could write this as one single logarithm. And the answer would be the log of what? You would take the variables c, a, b, I, n and multiply them. Am I right? C times a times b times I times n, and he would have log cabin. Thank you. I'll be here all week. No, not a true story. But it'd be fun if it was, right? But if you think about this, that is using that addition property of logarithms, right? Just on a much higher scale with 5 different logarithms. And that's the case, guys. You can use that with as many logarithms as you want. All right, so what about the subtraction property of logarithms? Well, as you can guess, the log base b of m minus the log base b of n is going to be the log base b of m divided by n. Right? And again, I'm going to go ahead and put that in parentheses. Not that I really have to in this case, but it does sort of set it off. And the same thing works for the natural log. Take little a divided by little b there. All right? I do not have a funny anecdote for that particular property. I'm sorry. But we are ready to move to the second page. Example 2. And it says, okay, let's now use our calculator and let's find the value of each of these logarithmic expressions. So we're about to stumble across another property, I bet. So what we have here is the log base 2 of 5 to the second power. So I'm going to go to my calculator and I'm going to clear all this junk. It's getting a little busy. And I'm going to type the log base 2 of 5 squared. Now I want to make sure that in case there's some ugly output, I'm going to make sure that there's a decimal in here so that I can avoid that. And my answer is 4.643. All right, or 4.644 if we want to round. All right, rounding and truncating are perfectly acceptable things to do on an advanced placement test. So 4.644 is what we're going to say. 4.644. They would like us to figure out what do we get if we take 2 and multiply it by the log base 2 of 5. So I will return to the calculator and I will say, let's take 2 and multiply by the log base 2 of 5. And the answer I get is, oh, smart alecky calculator, right? What did I forget to do? If I don't put a decimal, the calculator is going to compute an exact answer. That's why, that's why it's called a computer algebra system. So now if I put that decimal, I'm going to be okay. So we're going to get rid of this. And we can see that these two answers are indeed the same, aren't they? 4.644. Do you think you can stumble across a rule? What do you think? Where does it look like this 2 came from? Probably that exponent, right? And if we look here, the same thing has happened in part B. That exponent comes out in front of the logarithm. In part C, again, even with the natural log, this exponent comes out in front of the logarithm. All right? And I don't know if I necessarily need to type those in to verify. All right? I'm going to do the part C because it's just going to take a second. But if I use the same thing for the natural log, and that was the natural log of 5 to the second power, right, this gives me 3.219, but if I take the 2 out in front and just multiply that by the natural log of 5, it's the same result. So I'm going to write that one at least, 3.219. So we can now stumble across another property. And that property says if we have the log base b of a to the n, that is equivalent to n out in front times the log base b of a. Likewise, it works with the natural logarithm, n out in front times the natural log of a. Okay? Now, again, I'm going to bypass the part here that requests that we write in words what the property says. I'm not saying that that's a bad thing to do, but we could speak it at least, and we would just simply say that the exponent that's attached to your argument can come out in front as a multiplier of the entire logarithm in order for you to be equivalent. All right, we know enough to be dangerous. Example 3 is probably the most important example of this lesson because we're going to take all of these logarithm expressions, of which there are more than one, and we are going to consolidate them into a single logarithm. So if we read the directions, it says just that. Rewrite each expression as a rational number or a single logarithm. There might be some cases that these actually turn out to be a nice numeric value. All right. I think A might be one of those instances. So if we have the log base 2 of 6 plus the log base 2 of 8/3, what would be our first step? Write this as the log base 2 of 6 times 8/3. Does anybody know what 6 times 8/3 is? I believe that would be 24, would it? No, I don't know. I believe it would be 16, right? 6 times 8/3 would be 16. Now, is the log base 2 of 16 something that we can figure out? 2 to what power is 16? This is kind of what we're thinking. Right? 2 to what power is equal to 16? This is what I mentioned to my class a moment ago about walking across the bridge. And the answer would be 4, wouldn't it? 2 to the 4th power is 16. So this is an instance where the answer is actually a numerical value. But I don't think that's going to be the case in our future examples. So look at B. 1/3 times the log base 3 of x minus 2 times the log base 3 of y. Well, before we start consolidating this into a single logarithm, we have to make sure that this 1/3 coefficient is put in a different spot. And that spot would certainly be the exponent of the x. And we will do the same thing with the coefficient of the log base 3 of y. We are going to put that 2 as the power of the y. Right? The reason why we have to do that first, you guys, is if I go back a page to my property here at the bottom, the subtraction property of logarithms, notice that there's not a bunch of junk in front of the logarithms before this rule can be applied. So any coefficients in front, we have to remedy first, as we did. Now we can go ahead and use the subtraction property. So this can be written as a single logarithm in base 3, and we would have x to the 1/3. It's also okay if you write that as the cube root of x. Maybe it looks better, but I don't care. And then that's all divided by y squared. And you want to make sure that all of that looks like it's inside the logarithm. Maybe putting parentheses around it might help. But that's where you'd stop. Right? There's nothing more that you can do to this. All right? Let's take a look at C. We have 3 different logarithm expressions. They all have the same base. They don't seem to have a bunch of junk in front. So I think we're ready to start consolidating these. So we would have the natural log of. Well, notice our first sign is a plus between our 2 logarithms, which means the x plus 2 and the x can be written as a multiplication problem. But then our second sign is a minus, which says we would introduce a division bar, and we would put the x cubed in the bottom. Now, normally, I don't have a problem with that answer. This answer would be deemed correct, but let's say if this was a multiple choice problem, it's very likely that some simplification would be done, and that simplification is just simply reducing the x over x cubed, and this would be probably a little bit better answer. X plus 2 over x squared as our argument. That would be the choice that you'd want to circle. All right. So we got the first row done. You're going to find out that I'm going to work more of these with you because they're so important that I want to make sure that we're very proficient with them. All right, so let's take a look at D. Once again, we have more than one logarithm expression, but we also see that there's some unnecessary things written out in front of the middle logarithm. So I'm going to take care of that first. So I would have the log base 3 of x plus the log base 3 of 3 to the second power, well, there's no point of writing it as 3 to the second. You could, but let's just go ahead and square the 3 like we know and call it 9. And then we have the subtraction of the log base 3 of y. And now we have a very similar situation than we did in part C. One logarithm in base 3, the x and the 9 are going to get multiplied, and then we're going to divide all that by the y. And there's nothing more than you can do to simplify it. Okay. My students, even though we're recording, if you have any questions, make sure you let me know. All right. In fact, I'll tell you what I'm going to do. I'm going to pause the video. My class and anyone watching, let's go ahead and have you work parts E, F, and G on your own, and then we'll come back and see if you guys are correct. And we are back with the solutions to part E, F, and G of example number 3. For the most part, these looked similar to the previous problems that we looked at. If there's anything I wanted to point out, in E, it had a very unusual simplifying. Once you get to this part where you have x to the 5th over x to the half, we could go ahead and subtract the exponents. 10 halves minus 1 half would be 9 halves, and this is an acceptable way to leave the answer. And anything about F that was unusual, well, again, it just simply had this idea where we had a reduction of the x over x cubed that we could pull off. And after doing that, I thought I would just write the 2 in front of the x minus 3. And I think G is certainly the most interesting of these problems. And the reason it is because it's the first time that we saw 2 minus signs within our log expression. So what that means is we would actually divide twice. So that essentially means that the y squared and the z both will reside in the denominator. Now, if students have a hard time with this, sometimes I say, think of this as being written a little differently, and maybe this will help. We could write this as 1/2 natural log of x, which is still ln of x to the half. But what if I subtract and put a quantity in here, parentheses, which means I would be forced to use a plus sign right there. And then you can think of this as being one division action with a multiplication within that denominator. And that's what happened. Okay. So example 3 has got, 7 really good examples that illustrate the properties very, very well. Now, you might think, well, what's this example 4 all about? Well, it's the exact same cadre of properties. It's just that now we're going to move in the other direction. So we can see that the directions say rewrite each of the following logarithm expressions as multiple logarithms in expanded form. So you might have an answer that's got 2 logarithms, 3 logarithms, 4, just depends on the situation. So let's work a few of these together. So for our A, the log base 3 of xy squared. First thing that we note is that there is a multiplication going on between the x and the y squared. So we will split the logarithms using what sign? A plus. So we'll have the log base 3 of x plus, and then if you want to use more than one step, I guess the problem would look like this. Because by the time you split it like that, you might notice, oh, that 2 we could bring in front. Now, there's nothing in the problem that says you have to do that, right? We've already split this apart into 2 separate logarithms. But if this were a multiple choice problem, and let's say that this option here was nowhere to be found among the choices, but this option here was like choice C, it's certainly the option that you want to circle, right? No way would both of these show up as options in a multiple choice because they would both be correct. All right? So let's go ahead and operate under the assumption, I should say, that I want all exponents out in front of the logarithm. So for B, I would have the natural log of x I see that there's multiplication happening, plus, and then I have the natural log of y to the half, which means I could bring that 1/2 out in front, multiply by the natural log of y, and I've got it simplified the way that I've described. Okay, let's do C together, and then I'll pause the video. So for C, we've got the log base 2 of x cubed, but oh, darn it, I should have put that 3 out in front. Well, I can still do that. I'll put that 3 out in front right there. Actually, make it look like a 3 this time. And now I see a subtraction is going to be in our future because of the division that we see. And then I've got a 2 that's going to come out in front as the power of the y. And then, of course, the log base 2 of y. All right. Now, there are 4 more of these, very similar. Let's pause the video and have you try those on your own and check them in a moment. And we're back. Hopefully now you can take a moment to check your answers D, E, F, and G. Not a lot of strange things happening with either of these. The couple of things I might point out, first of all, with E, this quantity x plus 2 on top, a lot of students think that they can somehow break this apart. Students want to say, oh, well, isn't this the same as ln of x plus the ln of 2? Unfortunately, that is not a thing. You cannot do that. In fact, if you do that, you're assuming that x and 2 are being multiplied, right? So if anything, you're thinking that this is the natural log of 2 times x, and clearly that's not what we have up here. So the x plus 2 just simply has to stay together as a package deal, and we just put it in parentheses. Anything with f that's strange? Not so much. I mean, the 2 times the a might have been a little bit tricky for some of you, but the 2a is kind of, again, a package deal. I wouldn't have to put parentheses around this, but I certainly could if that made it a little bit more clear. And then G kind of goes back to the idea that we have 2 values that are inside of our denominator. So they're both basically results of division. So there would be 2 minuses in that problem, both preceding those logarithms. Now, the next part and final part of this lesson kind of hinges upon the last example 5, and pretty much this sums up why we do these properties. We learn these properties so that we can solve equations that have logarithms in them, because a lot of times equations out of the world of chemistry, out of the world of physics, have these logarithms inside of them, and we need to solve. So for example 5, it says solve each of the following equations for x by rewriting each side of the equation as a single logarithm. All right, sounds like what we just did in example 4. Then set the arguments equal to each other. And then in the boxes to the right, check the solution. If the equation has no solution, we would need to specify why. So we'll do a couple of these together. Now in part A, notice that we have 3 logarithms, and they are all common logarithms, therefore they are base 10. So on the left side, we can write this as a single logarithm by taking the x and multiplying it by 2 to the second power, which is a 4. So this is the log of 4x, or the log of x times 4, essentially. The right side has already a single logarithm. There's nothing to do. And we have a rule that says if you have a logarithm expression equal to the same logarithm expression, the same base that is, you're allowed to pretty much ignore the logarithm and just set the arguments equal to each other like the directions say. And now you've got a very easy Algebra 1 equation to solve. That will give you an answer of 3. Now, I'm reluctant to circle 3. I mean, what if it's not correct? What if this is a trick question? So I'm going to go ahead and use the space to the right to check the answer. And all that I need to do is basically replace the x with 3 anywhere I saw it in the problem. So I have the log of 3 plus 2 times the log of 2 equals the log of 3 plus 9. I can go ahead and call that 12. And if you look at the left side, we could break this down into a single logarithm by multiplying the 3 times the 2 squared. And before we know it, don't we have the log of 12 on the left side as well? So this is a good indication that our x equal 3 is the right answer. So I'm going to circle it. But kind of stay with me because sometimes on the right side on your check, some very weird things can happen. So we're going to move to the last page here of the notes. And we're going to do B together. So for B, we see that there's a subtraction on the left side. So I'm going to write this as the log base 3 of x minus 4 over 2 equivalent to, the right side has really nothing to do. It's already written as a single logarithm. Now that the two sides have the same single logarithm, we are allowed to set the arguments equal to each other. All right, I'm going to go ahead and call this x plus 1 a numerator over 1 so that maybe we can cross multiply a little easier. So x minus 4 would equal 2x plus 2 after we distribute. And then if I subtract x to the right and subtract 2 to the left, it looks like I got x is equal to negative 6. Looks pretty good, right? Don't want to circle it just yet. Let's check. So if we go to the left side, or I'm sorry, to the right side, and we insert negative 6 for our x, we would have the log base 3 of negative 10, that's interesting, minus the log base 3 of 2 equals the log base 3 of negative 5. What do you guys think about this? Does that look like it's legitimate? See, here's the problem. If we look at this and think, oh yeah, that's just a subtraction, so this is the log base 3 of negative 10 over 2, which, wait, that looks like the log base 3 of negative 5. Well, of course this is right. Well, guys, as it turns out, this is not right. X equal negative 6 is not a solution of this problem. And since it is the only answer that we got and it doesn't work, the answer to this is no solution. Now, I'm sure you're wanting to know why. What's the situation about the argument of a logarithm? Can we have a negative there? Now, we just said, oh, no, you can't have a negative there. But why? Well, let's go to the calculator, clear all this up, and talk about this. Let's clear this up. Whoop, let's clear it. Sorry about that. We're going to clear all this. And let's say, well, what if we have the log of negative 5? What do you think the answer is? Okay, the calculator does not seem to like that, does it? Error. We cannot have negative input into our logarithms. If we think about graphing, I don't know if you've ever thought about this. Anybody ever think about graphing a logarithm? Can it be done? Say the common log base 10 of x. It certainly can be done. Yep, it's a growth function, guys. But what do you notice about this equation? Does this equation have a domain that allows for negative x's to exist? No. So that's a great graphical reason as to why that's the case. And trust me, you're going to see this in droves later on because I think this is the focus of one of our future lessons. But the bottom line is going to be real simple, guys. If anytime during your check, if you see the log of a negative number, stop. Stop right there. Stop your check. Go back to your answer. Cross off that solution. And if it's the only solution, then no solution is what's left. All right? I'm going to pause the video one last time, and I'm going to ask that you guys work these last 3 problems and check them with me when you return. And for the last time, we are back. Hopefully you had some success working through C, D, and E. We're going to just break these down very quickly. For C, first of all, Nothing unusual with the way that we consolidated these two logarithm expressions, just did so with the multiplication. Now this problem did have something interesting happening towards the end. Notice that we have a quadratic that we had to factor and thus produces two answers of x equal -4 and x equal 2. It is sometimes possible that logarithm equations could have more than one answer, but we still have to check both of these. So when we check the -4, we immediately see that we have the log base 2 of -4 plus 2. And notice I put on the brakes right there. There's no need to do anything else because this is nonsense. And because of that, we can strike -4 as an answer, move on to check 2, which works out perfectly. We don't see any negative values inside of a logarithm. So 2 is good, which gives us the license to circle it. Now the answer to D had a pretty ugly result, 9/11, but that doesn't make the problem any more difficult to do. We start by seeing a subtraction between these two logarithms, so there's a division that must happen there. There's a plus between these two logarithms, so there's a multiplication that happens there. When we distribute the 3 in, we have 6x minus 3 on the right side. I put that over 1 so I could much more easily see the result of cross multiplication. If x plus 3 is going to be 12x minus 6, lo and behold, we'll eventually work our way down to x being 9/11. Now these are never fun to check because you would have to plug the 9/11 in for this x, as you can see over here. And notice I just kind of glanced at that. I didn't simplify it, but I just wanted to make sure that there was never going to be a negative result in our logarithm expression. When we go to our final example with natural logarithms, a very similar process where we cross multiply, solve the equation, and we get 12/7. And as I put the 12/7 in for my x, even right here, I can tell that I'm going to get a value that's still positive. 24/7 is bigger than 3, so I'm safe in that I'm not taking the log of a negative number. And as you can see over here, there's no negatives after our log. All right. Hopefully this video helped a little bit with your understanding of the properties of logarithms. And if you're interested in other videos I have in the future, we're going to be talking about the graphs of logarithms and other special applications. So anyhow, I'll see you next time.